of a perfect cube, or I can turn it into the face of an octahedron. So I can show the changing of these Platonic geometries. So the face of one becomes the corner of the other. Just the same way that self-assembly works in proteins, we have this formation of triangles, and they fold up to create this unique tetrahedron structure. So the folding of these triangles is called tessellation. And so what we're doing is we're tessellating these geometries from being in a single plane to coming into three-dimensional space. And so we're animating them. And the animation of these geometries allows you to map any topography. So you're able to map surfaces and turn them into solid forms. So this is something that's very unique to the ZOOB system. Is here again, these circles would fold up, in terms of an Archimedean geometry and make the great circles of a larger Archimedean structure like this. This isn't differentiated, but you still have those same circles that would intersect and create some of those classic Archimedean geometries. In the case of, say, this form, you can read it in a two-dimensional plane like an image. But the truth is that it actually starts to fold on its own and starts to connect itself in a different way and form this three-dimensional dynamic structure. And so as this starts to assemble itself, you start to get these larger self-assembly and functions. So here you have something that's this double helix, and you can see how dynamic this structure is. And it's just these simple rules added up over many iterations that allows you to see this larger function. And so this could be the way in which DNA works, or a protein, or things on a larger macro scale. But it shows you that not only do you create that primary relationship, like with stereotonic or tectonic things, where you're creating a form, but you also have a function. These are just triangles that are connected with another type of pedal connection. And as I pull on them, it creates a spring. So you have a tension spring. So this is just another type of pattern making that you'd find in an organic system, just the way that you'd find leaves or different types of stacking or different types of what I call fuzzy connections that over a larger number of them, or over a different kind of structure, you create a certain kind of dynamic and function. So here's a spring function. And here you have something where you have branching. You can see this larger idea that you could imagine that this could be the branching of leaves or a tree. You see that they're able to flip up and down in different relationships. Again, it's just a way of looking at different kinds of pattern language. And so here, again, are different kinds of pedal connections. And you can see that, whether it's like fingers or like branching on trees or leaves, palm frond, that you have a back scratcher. So the idea is that you're able to both create this structure, the secondary structure in this relationship of branching, but it also is able to be articulated and change that form. And this is what's one of the really unique things about ZOOB. So what I started to look at was different ways that you'd find other connections in natural systems. So what I started to look at, again, just the same way with the branching connections that we saw before, is there are other pedal connections that work to make something that's like a foot relationship. So you can branch like this as well. And with this type of other pedal connection, you can actually turn the pedals to go 90 degrees in one way, or you can actually take them and go back like this and connect them so they'll go in the opposite direction. So you're able to connect them like this. So there are three different ways in which this single pedal connection will go between the citroid and a full pedal, like that. So again, they're fuzzy connections. I mean, you can knock them off if you want to, but they're also strong enough so that you can support something like eventually the pedal connections for the feet of this, this kind of dinosaur or lizard creation. So adding up some of these relationships, you're able to create different types of, biomotion and biostructures. And then another thing that's unique about the system is the ability to weave. And so you can take this kind of pattern language, and here you see this classic fireman's weave. And by connecting that pattern over and over, you start to be able to get solid structures. So here you have this woven pattern like this. And it's very solid and rigid. It can even be like a floor mat. And then here, out of it, we did a project with Kate Spade and made these handbags one year for their line. And again, it's just simple weaving of something that you wouldn't expect maybe at first. Is you're able to see what you can do in terms of making different types of form and function. Here's another type. So that weave that I first showed you was a very solid weave, where this is a very flexible weave. This is like a herringbone pattern. And so you can fold this and be able to make a fabric out of it. And you can even turn it onto itself and make a Mobius strip. So it can have a single surface and describe that kind of, here you have a Mobius strip. And if you put your finger and run around the whole surface, there's only one surface. So it goes all the way around and back onto itself. And so, this is just something that's very unusual for something that has that kind of rigidity. And you can see all kinds of different secondary and tertiary behaviors with these kind of models. Here's another type of crossing over and weaving. You see this zigzag pattern. And this is, again, another way, like one of the basic structures of DNA is the double helix, which everyone's heard about. But another basic structure of DNA is called the alpha pleated sheet. And it's this kind of folding pattern that potentially can create different types of laminates. So this is, again, another type of basic subassembly. Back here I have this subassembly, which is like another type of woven pattern that is very similar to a sphincter, like a sea urchin or some kind of, sort of cyclical organic form. It's just woven. It has a very interesting sort of spring action to it. It has a certain kind of flexibility, and it comes from just a simple pattern making that I think I have over here. So you have something like this, where you have these 9 units that start the weave of this form. Again, as you continue that weave, you start to create this larger structure, and it can be made in all